Good morning, good afternoon, and good evening to everyone who joins us from around the world.
We're so glad you're here.
This is Andrew and Renee. Welcome to the Stack series.
It is wonderful to be back.
Today, we are exploring molecular sensors and the future of chemical perception.
This is a topic that sits right at the bleeding edge of what's possible in chemistry. We're really talking about engineering individual molecules to do jobs that, entire labs full of equipment used to do.
To see and smell the world in ways we just can't.
Better than we can.
Yeah.
Far better.
I want to set the scene here because when I started digging into this stack, my mind immediately went to science fiction. I mean, really.
It's hard for it not to.
Imagine a world where your smartphone can, taste your tap water and tell you right there in your kitchen if there's lead in it.
Instantly.
Instantly. Or imagine a little sticker on your skin, like a temporary tattoo, that can smell a change in your sweat and warn you of an impending asthma attack before you even feel a wheeze. Or a device that can smell a disease on your breath, long before you have a single symptom.
The reality is that isn't science fiction anymore. I mean, it's not on the shelf at your local store yet, but the science, the fundamental science is there. This is the field of molecular sensing or chemosensing.
So we're moving past this idea of, taking a sample, bottling it up, sending it to a lab, and then waiting a week for an email.
We're moving toward real-time molecular level perception. The information is generated right where and when you need it.
So our mission today is to understand how scientists are building these molecular spies, these structures designed to catch the invisible chemical culprits in our bodies, in our environment.
And it's really a mission of translation. That's the key word. We're translating a chemical event, one molecule bumping into another, into a signal that we as humans can understand.
A signal like light or an electrical current.
Exactly. And to do that, we have to move beyond the simple metaphors. You always hear about the lock and key mechanism.
Right. It's the first thing you learn in biology class.
And it's a good starting point. It's not wrong, but it's incomplete. Today we need to get into the nitty-gritty, the complex thermodynamics, the optical physics, and even the machine learning that actually makes these sensors work.
We have a massive stack of sources today. We are pulling from reviews on heavy metal detection, something called surface-enhanced Raman spectroscopy.
Which is a mouthful. We'll just call it SIRS.
SIRS, thank you. And then there's machine learning and diagnostics and the really foundational chemistry of what's called host-guest interactions.
That's where it all begins.
So let's start there at the very bottom. What exactly are we talking about when we say molecular sensor? How is it different from, say, a thermometer?
Well, the thermometer, even a digital one, is macroscopic.
Yeah.
It's measuring the average kinetic energy, the jiggling of trillions and trillions of molecules in a room. It's an aggregate measurement.
It's taking the temperature of the crowd.
Perfect analogy. A molecular sensor, on the other hand, operates at the limit of chemical interaction. It's designed to interact with one specific type of molecule, which we call the analyte. It's not interested in the crowd. It's looking for one specific person in that crowd.
So it's not measuring a general property like heat or pressure. It is actively hunting for a specific target.
Precisely. It's a hunter. And if you look at one of the main sources, advanced molecular sensing, they break down the architecture of these little hunters into three essential components. It's a tripartite architecture.
Okay, let's unpack that, because when I hear tripartite architecture, I'm thinking of a building. But we're building a molecule. What are the three parts?
Okay, so first you have the receptor. Some papers call it the recognition moiety.
That's the business end.
That's the business end. Think of this as the hand that is perfectly shaped to grab the target. This is the part that does the specific chemistry.
Okay, the hand. What's number two?
Number two is the signaling unit, or the transducer. This is the flare that goes off when the hand catches something. It's the part that converts that chemical grab into a physical signal we can actually measure, usually optical or electrochemical.
So light or electricity.
That's right.
And the third part?
The spacer.
The spacer. I have to be honest, that sounds like a boring connector piece. Is it really that important?
Oh, it is absolutely critical. It's the unsung hero. The spacer is the physical bridge that connects the hand to the flare. But it does way more than just connect them.
Okay.
It acts as an insulator and a communicator. It has to be designed just right. If the hand and the flare are too close, their electron clouds might interfere with each other. The flare might go off by itself, or the hand might not be able to grab properly.
A false positive.
A false positive. But if they're too far apart, the signal might not trigger when the hand actually grabs the target. the message gets lost.
So it's about spacing them just right. The communication happens, but the interference
You
doesn't.
got it. It's a delicate balancing act.
I keep coming back to the analogy of a doorbell system. It seems to fit perfectly here.
It's a classic for a reason. Go ahead.
The button you press outside is the receptor. It's waiting for a very specific input. Your finger, or in our case, the chemical target.
Yep.
The wire running through the wall, that's the spacer.
Mm-hmm.
And the chime that rings inside the house, that's the signaling unit, the flare.
Exactly. And you can see how each part is essential. If the button is broken, the guest can stand there all day and you'll never know. If the wire is cut, same problem.
Or, conversely, if the wire is faulty, it's shorting out.
The chime might ring constantly even when no one is there.
That's a false positive. And in medical diagnostics, that's a nightmare. Telling someone they have a disease when they don't.
It's a catastrophic failure.
Yeah.
So the magic really happens at the receptor with that initial handshake. And this brings us to the core concept of host-guest chemistry.
This sounds like the social life of molecules.
It really is.
Yeah.
We are dealing with non-covalent interactions here.
Okay, let's pause on non-covalent. Because usually when we talk about building molecules, we're talking about covalent bonds. Sharing electrons, fusing atoms together. It feels permanent, like welding steel.
That's a perfect description.
Huh.
Covalent bonds are the steel girders of chemistry. They are strong, permanent, and they take a lot of energy to break.
Yeah.
But host-guest chemistry, it relies on something much more subtle. It's about temporary handshakes.
Not a marriage, just a handshake.
Exactly. It relies on much weaker forces. Things like hydrogen bonding, electrostatic attraction, van der Waals forces. These are orders of magnitude weaker than a covalent bond.
So why use weak forces? If you want to catch a target, wouldn't you want to weld it to the sensor, just grab it and never let go?
Not always, because often you want the sensor to be reusable, or you want the binding to be reversible so you can measure concentrations going up and down. If you weld the target to the sensor, first, you've now changed the chemical nature of the very thing you're trying to measure. And second, your sensor is now a single-use item. It's done. You want to hold the target gently, identify it, and then maybe let it go.
So the sensor, the host, has to be designed to shake hands with only one specific guest, using just the right amount of force from all these little interactions combined.
Correct, and this is where that lock and key metaphor comes from. The host must be complementary to the guest in three ways: size, shape, and electronic character. If the glove doesn't fit, you don't get a signal.
Let's talk about the cast of characters here, because the chemists who designed these hosts have come up with some incredible shapes and, frankly, some pretty wild names for these synthetic receptors. It sounds like a molecular zoo.
It absolutely is a zoo. One of the classic groups, discovered way back in the 60s by Charles Peterson, is the crown ethers.
Crown ether.
They're basically cyclic rings. Think of a donut that are studded with oxygen atoms on the inside of the ring. And they absolutely love to trap alkali metals.
Like potassium or sodium from our own bodies.
Exactly. Imagine a specific crown ether as a donut, where the hole is exactly the size of a potassium ion. The oxygen atoms line the inside of the ring, and they're electronegative. They have a partial negative charge.
And potassium is a positive ion.
So opposites attract. The positive potassium ion slips into the negative hole and is held there by all these little electrostatic handshakes with the oxygens.
But why is it a lock? Why doesn't it just grab anything positive that floats by?
Because of the size. It's all about the fit. If you try to put a sodium ion in that same hole, it's too small. It rattles around. It can't touch all the oxygen atoms at once, so the combined grip is very weak. It falls right out.
Then if you try to put a bigger ion in, like cesium?
It's too big. It won't fit in the hole. It's the Goldilocks principle of chemistry. Not too big, not too small, but just right.
I love that. Geometry dictates chemistry. Okay, so that's rings. Then we have calixarenes.
Calixarenes are named after a Greek vase, or chalice, a calyx. They're literally bowl-shaped molecules. And the amazing thing about them is that they're tunable. You can chemically modify the upper rim of the bowl and the lower rim of the bowl to change what it likes to eat.
So you can decorate the bowl to make it attract different guests.
Precisely. You can put groups on the rim that are good at hydrogen bonding, or groups that are negatively charged to fine-tune its selectivity for a specific target.
And then we get to the ones that really caught my attention because of the consumer connection, cyclodextrins.
Ah, the workhorses. They are fascinating. Cyclodextrins are made of sugar molecules linked together in a ring. They look like a truncated cone or a bucket.
The sugar bucket.
A sugar bucket, exactly. And because it's made of sugar, the outside of the bucket is covered in hydroxyl groups, so it loves water. It's hydrophilic. But the inside of the bucket is made of the hydrocarbon backbone of the sugar rings. It's greasy, it's hydrophobic, it hates water.
So you have the structure that's water-soluble on the outside, but has a greasy, water-hating pocket on the inside.
You got it. So they are fantastic for trapping greasy molecules inside that sugary bucket. They're used a lot in drug delivery, for example, to carry drugs that don't dissolve well in water.
But you told me before we started that I probably have these in my house.
You almost certainly do. In a can of Febreze.
Wait, Febreze is molecular sensing? Or at least molecular trapping?
It is host-guest chemistry in a spray bottle. Febreze uses cyclodextrins. When you spray it on your couch, the bad-smelling molecules, which are usually greasy, volatile organic compounds, get trapped inside the hydrophobic bucket of the cyclodextrin.
So it's not just covering up the smell with perfume, it's physically imprisoning the stink molecule.
It cages it. That's the technical term, encapsulation. Once the smelly molecule is inside the bucket, it's no longer volatile. It can't fly off the fabric and into your nose, so you don't smell it anymore.
That is mind-blowing. That is incredibly sophisticated chemistry happening in the laundry aisle. Okay, one more shape from the zoo. Cucurbiturols.
My personal favorite, they are pumpkin-shaped molecules.
Pumpkin-shaped.
Really? Literally. Cucurbita is the Latin name for the gourd family, which includes pumpkins. These molecules have this rigid, hollow cavity with two portals on either side. Guests can slide in, but the portals are lined with these electronegative oxygen atoms that can grab onto positively charged parts of the guest.
They're just beautiful structures. So we have rings, bowls, buckets, and pumpkins. But building these traps, it can't just be about shaping them like Play-Doh, right? There has to be a huge energy cost involved.
Oh, absolutely.
And this is where the sources started talking about entropy. And I'll be honest, my brain started to hurt a little. I had to read that section twice.
This is where we get into the thermodynamics of capture. It's the why behind the structure. And we have to talk about the entropy problem.
Entropy, the measure of disorder.
Yeah.
Second law of thermodynamics. The universe tends toward chaos. My desk tends toward chaos. Molecules tend toward chaos.
Exactly. Molecules, especially long chain-like molecules, love to be floppy and free. They have a huge number of degrees of freedom. They can wiggle, twist, turn, vibrate in countless ways. They have high entropy. They are happy being messy.
Okay, so let's take one of those floppy chain molecules. Let's call it a podand, I think the paper said.
Yes, and a cyclic host.
So if you want that floppy chain to wrap itself around a specific target, you have to force it to stop wiggling. You have to freeze it into a very specific shape.
And nature hates that. Nature taxes you for creating order. Forcing that floppy molecule to freeze into a specific shape to catch a target costs a huge amount of energy. We call it an entropic penalty.
So it's a bad deal. If the energy cost of organizing the molecule is higher than the energy you get back from binding the target,
the binding simply will not happen. It's thermodynamically unfavorable. You'd be spending $100 to make 10.
So it's a terrible business deal. How do we solve this? How do we make it a good deal?
We cheat. Or rather, we pay the cost up front. This is a concept called pre-organization, and it leads to what's known as the macrocyclic effect.
Pre-organization.
Instead of building a floppy chain that has to organize itself around the target every single time, we build the trap as a rigid ring, a macrocycle, from the start.
So the trap is already in the shape needed to catch the guest. It's pre-organized.
Right. Think of it this way. It is so much easier to park your car in a pre-built garage, that's the macrocycle, than it is to build the entire garage around your car every single time you want to park.
Okay, that makes perfect sense. The floppy chain is like a pile of bricks and wood. The macrocycle is the finished garage.
Precisely. And you pay the energy costs, the effort of building the garage during the chemical synthesis of the sensor in the lab. That's the entropic prepayment.
So the chemist does the hard work in the flask. They force the bonds to form the ring. They pay the entropy tax once during synthesis.
Yes. So when the finished sensor is finally floating around in the water or the blood, it's already rigid. It doesn't lose much freedom when the guest arrives because it didn't have much freedom to begin with. The entropic penalty is tiny.
That makes the binding event spontaneous and favorable.
Exactly.
But there's another layer here, another hidden cost. The sources kept mentioning solvation.
Ah, the hidden actor in almost all biological chemistry. Water.
Water is everywhere?
And water is sticky. It's a polar molecule. It forms hydrogen bonds with everything. So your host molecule isn't naked in the solution. It's covered in a tightly bound shell of water molecules.
And the guest.
The guest is also covered in its own shell of water molecules. They're both wearing water coats. For them to shake hands, for them to bind, they have to take off their coats.
And that must take energy. You have to break the bonds between the molecule and the water.
It does. It's another energy cost. You have to pay energy to desolvate them and strip the water off. But, and here's the beautiful counterintuitive twist, when you release those water molecules from the surface of the host and guest, where do they go?
Back into the bulk liquid, the
Yeah.
rest of the water?
Exactly. They go from being stuck on a surface, ordered and constrained, to floating freely in the ocean of other water molecules. They go from being ordered to being disordered.
So the water molecules themselves gain entropy.
Massive amounts of it. A huge gain in entropy. And since the universe loves increasing entropy, this release of water actually provides a powerful driving force for the binding event.
Wait, so you're telling me the reason the sensor catches the target isn't just because they are attracted to each other. A big part of it is that the water wants to be free.
In many, many cases, yes. The famous hydrophobic effect, which is the reason oil and water don't mix, the reason our cell membranes form, the reason proteins fold, it's largely driven by the water molecules wanting to maximize their own entropy. The host and guest coming together is just a convenient way to liberate the water.
That is a fundamental shift in how I view this. It's not just a simple magnetic attraction. It's a complex thermodynamic transaction where the solvent is a key player.
It's a complete ecosystem, a delicate balancing act of forces and energies.
Okay, so we've built our trap. It's a pre-organized pumpkin. We've paid the entropy tax. The water has been liberated. The host has caught the guest. But how do we know? If a molecule catches another molecule in a beaker, it doesn't shout. How does the doorbell ring?
We need to turn that chemical event into light. And this brings us to the fluorescence mechanisms. The most common one, and in my opinion the most elegant, is PET, photo-induced electron transfer.
This is often described as a molecular on-off switch. But how does the switch actually get flipped at the atomic level?
Okay, let's break it down. Imagine a normal fluorescent molecule, a fluorophore. When you shine light of the right color on it, an electron in that molecule absorbs the energy and jumps up to a higher energy level. It's now in an excited state.
It's energized.
Right, but that state is unstable. It wants to come back down to its comfortable ground state. When the electron falls back down, it has to release that extra energy it absorbed. It does so by spitting out a photon of light. That's the fluorescence we see.
Simple enough. Excitation, relaxation, emission.
Right. But in a PET sensor, we deliberately mess with that process. We attach our receptor, the hand, to the fluorophore, and we design that receptor so that in its empty state, it has a high-energy electron that's just itching to go somewhere.
Okay.
Now, when our fluorophore gets excited by light and its electron jumps up, it leaves a hole, a positively charged empty spot in the lower orbital it came from.
An empty seat.
An empty seat, exactly. Now, normally, the excited electron would just fall back into that seat and emit light. But in our PET sensor, that high-energy electron from the empty receptor sees the empty seat and zips over to fill it first.
It jumps the line.
It jumps the line. This is the electron transfer part. It fills the hole. So now, the original excited electron is stuck upstairs. It has nowhere to fall back to. You can't emit a photon of light. The energy just dissipates as heat. The sensor is dark. It is off epioia. This is called quenching.
So, to summarize, empty sensor equals electron stealing, which equals no light.
That's the logic. But when the target binds,
When the guest binds to the receptor.
the target, let's say it's a positive metal ion, comes in and interacts with the electrons in the receptor. It holds on to them, it lowers their energy, it makes them busy. They're no longer high energy enough or free enough to jump over and steal the seat in the fluorophore.
So the seat stays open for its rightful owner.
The seat stays open. And so the fluorophore works as nature intended. The excited electron falls back down into its own hole, emits a photon, and the light turns on.
So target binds equals electrons get busy, which equals light turns on.
That is the mechanism. It's a beautiful molecular logic gate. If target is present, then emit light.
And there are other ways to make the light change, right? The sources mentioned FRET.
FRET, yes.
Okay.
Fluorescence resonance energy transfer. That's more like a wireless energy transfer. Imagine you have two different colored dyes, a donor and an acceptor. The donor absorbs light and gets excited.
Okay.
If the acceptorite is very close by, instead of emitting its own light, the donor can just transfer its energy directly to the acceptor, like passing a baton in a relay race. Then the acceptor emits its own different colored light.
So the color of the light tells you how close the two dyes are.
Exactly. So you can design a sensor where binding a target causes a shape change that brings the two dyes closer together or pushes them further apart, and you see a change in the color of the light.
And what about ICT? Intermolecular charge transfer.
That's a bit more complex. It involves designing a fluorophore, where the electron distribution, the charge, shifts across the whole molecule when it gets excited. When your target binds, it can pull or push on that electron cloud, which changes the energy of the excited state.
Which changes the color of the light it emits.
Right. So your sensor might go from glowing blue to glowing green as you add more target. This is really powerful because it's ratiometric. You can measure the ratio of blue light to green light, which is much more accurate and less prone to error than just measuring how bright the light is.
And finally, the really cool one, chemiluminescence.
The firefly one.
Right, no laser needed.
No external light source at all. The chemical reaction between the sensor and the target itself generates the light. In a glow stick, you snap the capsule, two chemicals mix, and they create a high-energy intermediate molecule that then relaxes by emitting a photon.
So you could design a system where that reaction only happens if, say, a certain toxin is present.
Precisely. You mix your sample with the sensor reagents, and if the sample starts glowing in the dark, you know your target is there. It's incredibly sensitive and requires very simple instrumentation.
So we have the foundations. We've got the lock, the key, the pre-built garage, the water tax, the electron musical chairs. It sounds, on the surface, like it's a solved problem.
It does, doesn't it?
But as we dig deeper into the forces, it becomes crystal clear that it is not all smooth sailing. There are some major fundamental debates and trade-offs in this field.
We are very far from solved. I would say the biggest battlefield right now is the constant tension between sensitivity and selectivity.
The great trade-off.
It's relatively easy to design a sensor that is very sensitive, one that detects something at a very low concentration. But real life isn't a beaker of pure water. It's blood. It's wastewater. It's a chemical soup, as you called it.
And in that soup, you have millions of other molecules, and some of them look very, very similar to your target. You mentioned sodium and potassium earlier.
It's a classic example. They are right next to each other on the periodic table. They both have a +1 charge. They're almost the same size. They behave very similarly chemically.
But in the body, their balance is critical for nerve function.
Absolutely critical.
Yeah.
But if you want to detect potassium in blood, you have a massive problem. The concentration of sodium in blood is often 30 times higher than potassium. So if your sensor is even slightly non-selective, if it binds to sodium just 5% as well as it binds to potassium,
the signal from the sodium will completely drown out the signal from the potassium. It's all noise.
it's all noise. This is the interference problem. And so the big debate is, how do you solve this? Do you spend years and years trying to engineer the perfect lock and key receptor that only fits potassium and rejects every single one of those billions of sodium ions?
That's the sniper approach. You build a hyper-specialized tool for one single job.
And for decades, that was the holy grail. Synthetic chemists would spend their entire careers trying to add just the right chemical group to a calyxarine to make it 1,000 times more selective for target A over its interfering cousin, target B.
But there has to be another way, right? Because nature doesn't always use snipers.
Right. Think about your own nose, your sense of smell. You can distinguish between the aroma of coffee and the scent of a rose. Do you think you have a specific receptor in your nasal cavity that is shaped exactly like a single coffee molecule?
No, I assume not, because coffee isn't one molecule, it's hundreds of different volatile compounds.
Exactly. And your genome doesn't have enough space to code for a unique receptor for every single smellable molecule in the universe. It's impossible. Instead, nature uses what we call the chemical nose approach, or differential sensing.
Okay, so what is that?
You have an array of different receptors, none of which are perfectly selective. Receptor A might bind a little bit to the coffee molecules and a lot to the bacon molecules. Receptor B might bind a lot to coffee and only a little bit to bacon. Receptor C might bind moderately to both.
So it's not about a single sensor giving a yes or no. It's about the pattern of responses across the whole array.
It's a pattern. It's a chord, not a single note. Your brain takes the combined signals from receptors A, B, and C and says, that specific combination of high, low, and medium signals, that signature means coffee.
So the debate in the field is, should we stop pouring all our effort into building the perfect sniper scope and instead build a choir of imperfect sensors and just let a computer figure out the song?
That is the debate in a nutshell. It's a philosophical battle between better chemistry, the perfect lock and key, and better data processing, the array and machine learning. The array approach is often cheaper and more versatile, but it requires serious computational power and can be fooled if the pattern isn't truly unique.
This issue of complex environments leads directly to another huge challenge, the reversibility problem. This one really stood out to me because of the clinical implications.
It is a massive hurdle for in-body sensing. Most of the molecular sensors we have today, think of the ones you might buy at a pharmacy, are what we call suicide probes.
That sounds dramatic.
It just means they bind once, they signal, and they're done. They are single use. The chemical reaction that produces this signal is irreversible. A pregnancy test strip, a pH strip. Once it turns color, you can't use it again.
And that's fine if all you need is a snapshot in time. Am I pregnant right now? Is this liquid acidic right now? But what if you're a diabetic?
Exactly. If you need to monitor your glucose or insulin levels continuously every minute of every day, a suicide probe is useless. You need a new sensor every minute. You need a video, not a single photo.
But making a sensor that can bind and then release is incredibly hard. And the problem, paradoxically, is that some of our best binding molecules like antibodies are just too good at their job.
They bind too tightly. An antibody is a molecule designed by billions of years of evolution to grab onto a virus or a bacterium and never ever let go until the rest of the immune system can come and destroy it. The binding affinity is astronomical.
The SOLAB source we looked at calls this the antibody limit. If the sensor grabs a glucose molecule and never lets go, you can't measure a drop in concentration.
Right. Imagine your glucose level is high, so all the sensors get filled up and they signal high. Then your body releases insulin and your glucose level drops. But the sensors are still holding on to the old glucose. They're still screaming high when the reality is now low. That's incredibly dangerous.
So what's the solution? How do you engineer a weaker grip?
We need to engineer receptors that are more like molecular pendulums or switches. We need them to grab the target, hold it just long enough for the signal to be generated, a split second, and then release it. We need to establish a dynamic equilibrium where the rate of molecules binding equals the rate of molecules unbinding.
It sounds like trying to catch a fish, weigh it instantly and throw it back, and doing that thousands of times a minute.
That is a great analogy.
Yeah.
And achieving that at the molecular scale means tuning the thermodynamics of binding to be on a razor's edge. You can't have a deep energy well where the gas falls in and gets stuck forever. You need a shallow well. But if it's too shallow, you'll never catch it in the first place.
A razor's edge. And even if you solve that, you run into the gunk problem. Biofouling.
The enemy of all implantable devices. The moment you stick any foreign object, a sensor, a catheter, an implant into the body, the immune system declares war.
It attacks it.
It coats it. Proteins from your blood albumin fibrinogen instantly start sticking to the surface. It's like barnacles growing on the hull of a ship.
And if the surface of your sensor is covered in a layer of protein barnacles?
The target molecule, your glucose or whatever, can't physically reach the receptor, the sensor goes blind. Within hours, or at best a few days, most implantable sensors lose their sensitivity because of biofouling.
The debate here seems to be about whether we can engineer stealth surfaces that can repel this gunk. I've read about things like shark skin-inspired coatings or zwitterionic polymers.
Yes, there's a huge field of material science dedicated to creating non-fouling surfaces. Materials that mimic the outer layer of our own cells or create a very tightly bound layer of water that proteins can't penetrate.
But nature is persistent.
Nature usually wins. So the other side of the debate says, maybe we should stop trying to fight this battle inside the body. Let's give up on implantables for now and focus on non-invasive sensing.
Sensing from the outside, looking through the skin.
Exactly. Which brings us to the great platform debate. Optical versus electrochemical.
Okay, so optical sensing using fluorescence, like we discussed, is fantastic for sensitivity. You can detect single molecules. It's great for imaging cells in a petri dish.
It is. But try doing it through your arm. Blood and tissue are turbid. They're cloudy. They scatter light like crazy. If you shine a flashlight through your hand, you don't see your bones. You just see a diffuse red glow. It's very hard to get a crisp, clear signal from deep inside the body using light.
Whereas electrochemical sensors,
They're the workhorses. The continuous glucose monitor that diabetics wear is electrochemical. It's essentially a tiny electrode that measures a current generated by a reaction with glucose. It's cheap to make, it can be miniaturized, and it works perfectly in dirty, opaque fluids like blood. Electricity flows just fine through tissue.
but it requires physical contact. The electrode has to be in you. You can't do it from a distance.
Correct. You need a wire, or at least a tiny needle, in the body.
Yeah.
So the trade-off is clear. Electrochemical is winning the race for point-of-care devices right now because it's cheap, robust, and manufacturable. But optical is still the king for research and ultra-high sensitivity applications.
This feels like the perfect pivot point to the frontiers section. We've talked about what we know and what we're fighting about. Now let's talk about the technologies that might just change everything. And I have to start with Ceres,
Surface-enhanced Raman spectroscopy.
the megaphone of chemistry. But I want to go beyond the metaphor. What is physically happening to create that megaphone effect?
Okay, to understand SIRS, you first have to understand regular Raman scattering. It's a bit mind-bending. When you shine light, which is made of photons, at a molecule, most of those photons just bounce off elastically. Same energy in, same energy out.
Okay, like a ball bouncing off a wall.
Exactly. But a tiny, tiny fraction of them, like 1 in a million, do something different. A photon will hit a chemical bond in the molecule, and instead of just bouncing, it will transfer a little bit of its energy to the bond, causing it to vibrate faster.
So the photon loses a little bit of energy.
Precisely. It bounces back with slightly less energy, which means it has a slightly different color. And the exact amount of energy it lost is a fingerprint for the bond it hit. A carbon-hydrogen bond vibrates at a different frequency than a carbon-oxygen bond. So by looking at these color shifts, you can get a unique vibrational fingerprint of the entire molecule.
But the signal is incredibly weak, 1 in a million.
It's absurdly weak. For most applications, it's totally useless. It's like trying to hear one person whisper in a sold-out football stadium.
So how does SIRS turn that whisper into a scream?
We cheat. We introduce a rough metal surface, usually made of gold or silver nanoparticles. When the laser light hits these metal nanoparticles, it excites something called a surface plasmon.
Plasmon, what's that?
The plasmon is the collective, synchronized oscillation of all the free electrons on the surface of the metal. Imagine the sea of electrons on the surface of the gold sloshing back and forth in perfect rhythm with the incoming light wave.
Okay, a sea of sloshing electrons.
This sloshing creates an incredibly intense, localized electromagnetic field right at the sharp edges and corners of the nanoparticles. We call these hotspots. If your target molecule happens to be sitting in one of these hotspots, it gets blasted by this massively amplified field.
And that amplified field boosts the Raman signal.
It boosts it by an almost unbelievable amount. We're not talking about making it twice as loud or 10 times as loud. We're talking about enhancement factors of 10 to the power of 6, 10 to the power of 8, sometimes even up to 10 to the power of 14.
A trillion times louder.
It can be, yes. It allows you to reliably detect a single molecule.
And the beauty of this is that it's label-free.
That's the holy grail. You don't need to attach a fluorescent tag or any kind of flare. You are reading the intrinsic vibrational fingerprint of the molecule itself. You're seeing the molecule as it truly is, just amplified by the plasmonic megafilm.
The applications for this that were listed in the sources are just wild. The idea of a liquid biopsy.
This is a game changer. Tumors shed tiny little vesicles called exosomes into the bloodstream. With SIRS, you can take a single drop of blood, find these exosomes, and read the spectral fingerprint of the proteins on their surface. You could potentially detect lung cancer or colon cancer from a blood test, long before the tumor is big enough to be seen on an X-ray.
And Alzheimer's.
The same principle. Looking for biomarkers like amyloid beta or tau proteins in cerebrospinal fluid, or even blood, years before cognitive symptoms arise.
And the one that really stood out, given recent history, was the COVID-19 breathalyzer.
Yes, the recent trends in SIRS paper covers this. A device you can breathe into, and the SIRS substrate inside captures viral particles from your breath. It can then detect the unique spectral signature of the viral proteins in under 5 minutes, with over 95% sensitivity. Nose swab up the nose, just breathe.
But there's a catch, isn't there? I looked at some of the raw SIRS spectra in these papers. They don't look like a nice clean barcode. They look like a jagged mountain range drawn by someone with a very shaky hand.
They're incredibly noisy and complex. You have hundreds, sometimes thousands of peaks. And because your sample is complex like breath or blood, you don't just see the virus. You see peaks from water vapor, peaks from normal proteins, peaks from pollutants you inhaled. The human eye cannot look at that mess and distinguish the mountain range of a healthy person from the mountain range of a sick person. They looked 99% identical.
Enter machine learning.
This is the perfect synergy that is unlocking the potential of SIRS. We are feeding these incredibly complex, messy spectra into sophisticated AI algorithms, support vector machines, convolutional neural networks, things like that.
So the AI looks at the entire mountain range at once and finds the subtle patterns.
It finds the hidden correlations that no human could ever spot. It might notice that in all the cancer samples, peak number 432 is consistently 0.1% higher relative to peak number 894, while peak 1204 is shifting slightly to the left. It sees the whole picture.
It's finding the needle in a stack of needles.
Exactly. There's a stunning example where researchers use deep learning plus SIRS to distinguish between different strains of bacteria, including drug-resistant versus drug-sensitive strains. To the human eye, the spectra were identical. To the AI, they were completely distinct. It achieved 100% classification accuracy.
That is just incredible. But is there a risk of overfitting? Of the AI learning the wrong thing?
A huge risk. That's the biggest challenge in this space. If you only train your AI on a small set of samples from your own lab, it might learn to recognize some random artifact like the temperature of your room or the specific batch of gold nanoparticles you used instead of the actual disease signature. You need massive, diverse, well-curated data sets to train these models robustly.
So the bottleneck is shifting from the chemistry to the data science.
In many ways, yes.
Right.
The future is in the algorithm as much as it is in the nanoparticle.
Another frontier material that kept popping up in the stacks was MOF's metal organic frameworks. You called them sponges.
They are the ultimate chemical sponges. Imagine a molecular tinker toy set where the hubs are metal ions and the connecting rods are organic molecules called linkers. By choosing different metals and different linkers, you can build these vast, three-dimensional crystalline structures that are mostly empty space.
They're porous.
Extremely porous.
Yeah.
With a tunable pore size and incredible surface area.
How incredible are we talking?
A single gram of a MOF, an amount that would fit in a sugar cube, can have an internal surface area of a football field.
I'm sorry, you have to unfold that for me. A sugar cube has the surface area of a football field. How is that physically possible?
Because it's almost all surface. It's an intricate lattice of pores and channels. Gas molecules can go inside and sit on the surface of every single strut and node within that crystal.
So they're absolutely amazing at trapping gases.
Unbeatable. We're seeing MOF-based sensors that can detect pollutants like nitrogen oxides or toxic industrial gases at the parts per billion or even parts per trillion level. The gas gets concentrated inside the MOF, allowing the sensor to detect it.
And why does that matter for the average person?
Asthma management is a huge one. Nitric oxide is a key biomarker of inflammation in the airways. If you can integrate an MOF sensor into a small handheld electronic nose, an asthmatic person could breathe into it each morning and know exactly how inflamed their lungs are. They could adjust their medication proactively before they have an attack.
So far, we've mostly talked about sensors that output data to a screen, a number on a computer. But one of the most fascinating papers in our stack was called The Outputs of Molecular Sensors Detectable by Human Senses.
This is where we get into what I call sensory bypassing. Why do we need a digital intermediary? Why do we need a screen and a graph? Why can't the molecule just tell us directly using the senses we already have?
We're talking about sensors that you can smell, taste, or touch.
Exactly. We are so reliant on vision in this field, a color change, a light turning on. But what if the user is visually impaired? Or what if you're a miner in a dark tunnel and you can't see a screen?
Or what if you just want to know immediately without having to pull out your phone?
Imagine a passive sensor for a toxic gas leak in a factory. Instead of a beeping alarm that requires batteries, the sensor is a material that, upon detecting the gas, catalyzes a reaction that releases a very strong, unpleasant odorant like the smell of rotten eggs.
Like the ethyl mercaptan they add to natural gas so you can smell it.
Precisely. But here, the sensor creates the smell only when the target is found. You smell the danger directly. Your own nose becomes the alarm.
Or taste.
There's some incredible research into smart packaging for food. The plastic wrap could be embedded with the sensor for spoilage amines, the chemicals that are produced when fish or meat starts to rot. When the sensor detects them, it releases a tiny, harmless, but intensely bitter compound onto the surface of the food.
So you take a tiny taste and your own body warns you instantly, do not eat this.
It co-opts your built-in evolutionary aversion to bitterness to protect you from food poisoning. It's brilliant.
And touch. How would that work?
This is huge for accessibility. You can create hydrogels that change their physical properties. Imagine a test strip for water quality that a visually impaired person could use. They dip the strip in the water, and if a certain contaminant is present, the hydrogel on the strip cross-links and becomes stiff and hard. If it's not present, it stays soft and slimy. They can literally feel the result of the chemical test.
That's such a human-centric way of thinking about this technology. It's not just data, it's a direct experience. And speaking of accessibility for everyone, we have to talk about the smartphone revolution.
The lab in a pocket.
It's true. Almost everyone on the planet has a supercomputer with a high-definition camera in their pocket.
And that camera is fundamentally a portable spectrophotometer. It captures light, it perceives color, with incredible precision. So we're seeing this explosion of 3D printed attachments, little clips that snap over the phone's camera lens.
And what do they do?
They hold a simple colorimetric test strip in a perfectly aligned position. You put a drop of water on the strip, which is designed to change color in the presence of, say, mercury or lead. The camera takes a picture under controlled lighting from the phone's flash.
And the app analyzes the color.
The app does the heavy lifting. It can analyze the exact hue, saturation, and brightness of the color on the strip. It can subtract the ambient light, correct for the camera's specific sensor bias, and compare it to a calibration curve. It can give you a quantitative reading, 75 parts per billion, that rivals a $50,000 laboratory instrument.
This brings us squarely into the implications of all this, because when you put a chemical laboratory in everyone's pocket, you don't just change science, you change society.
Absolutely. Let's start with environmental justice.
Heavy metals, lead, mercury, cadmium, they don't degrade. They accumulate in the food chain, in the soil, in the water. We've all seen the crisis in places like Flint, Michigan.
And historically, the power dynamic in those situations is incredibly skewed. A community suspects their water is poisoned. They have to lobby the government. They have to wait for an agency to come out and take samples. Those samples get sent to a central lab. It takes weeks, months. The data is often hard to access or understand.
But with cheap, portable, smartphone-based sensors,
A community can test its own water. A group of neighbors can test the soil in their own backyards. They can generate their own data, create their own map of the contamination in real time. It empowers people to walk into a town hall meeting and say, look, we have the proof right here. This is not anecdotal. This is data. It completely shifts the power dynamic.
it democratizes analytical chemistry. It turns citizens into scientists.
It does. But it also introduces a whole new set of anxieties. This brings us to the quantified self problem.
The flip side of the coin. If I can continuously monitor every neurotransmitter in my brain, every metabolite in my blood, every toxin I breathe in at the parts per billion level, am I going to go crazy?
It's a real question of information overload. Just because you can measure something doesn't mean it's clinically relevant or actionable. We live in a chemical world. There are trace amounts of toxins everywhere. If your phone buzzes to tell you that you just breathed in a single molecule of benzene while filling up your car, does that help you? Or does it just create a new form of digital hypochondria?
We have to learn how to interpret risk in a world of near-perfect information.
We do. We'll need a new kind of literacy to distinguish between what is detectable and what is dangerous. As our sensors get more and more sensitive, everything becomes detectable. We will need the wisdom to know what actually matters.
Another major implication that the sources point to is the rise of theranostics.
A beautiful portmanteau, a blend of therapy and diagnostics.
The idea that the sensor is the doctor. It doesn't just diagnose, it treats.
Exactly. Imagine a smart nanoparticle circulating in your bloodstream. Its surface is covered with sensors. Maybe something called a molecularly imprinted polymer, or MIP, which is like a custom-made plastic antibody. It's designed to look for one specific protein that is only found on the surface of a cancer cell.
Okay, so it's hunting for cancer.
It's hunting. And when it finds a cancer cell and binds to it, it doesn't just send a signal to a computer outside the body. The binding event itself triggers a conformational change in the nanoparticle.
A shape change.
A shape change that opens up a pore and releases a powerful chemotherapy drug right there, directly onto the tumor.
So it only treats you when and where you are sick.
That's the dream. It minimizes side effects because the toxic chemo drug isn't floating around your whole body killing healthy cells. It's a smart bomb. It's a material that senses, computes, cancer cell detected, and actuates, releases drug, all in one package.
That is the ultimate goal of personalized medicine.
It truly is, treating the disease at the single cell level in real time.
And finally, we have to look to the far future, the really sci-fi end of the spectrum, molecular robotics.
This is where we look maybe 50 years into the future. We're talking about devices built from the bottom up, from individual molecules that don't need electricity or wires. We're talking about molecules that can sense, compute, and actuate all on their own.
Molecules that think.
In a very primitive logical way, yes. A molecular robot that detects a toxin, processes that information through a series of chemical reactions that act as a logic gate, and then physically moves to block a receptor or releases an antidote.
Bypassing the computer and the smartphone entirely, the molecule itself talks directly back to the biology.
Or back to the human. It could be a system that communicates directly with your human senses, like the taste and smell sensors we talked about. A molecular robot that warns you of danger by making you taste something better, bypassing the digital world completely. It's a direct interface between the molecular world and the human experience.
It's a dizzying future, but one that is being built, literally, one molecule at a time. It all comes back to that core mission, making the invisible visible.
And that is what makes this field so profoundly exciting. We are building the tools to perceive the world and ourselves at its most fundamental layer.
Before we wrap up, thank you to all our partners, sponsors, and scholars who made this podcast and the research possible. We're truly grateful for your support.
And to our listeners, thank you for being part of this journey with us. If you enjoyed today's episode, be sure to subscribe and follow Stack Studios for more informative content, and support us on Patreon.
Until next time, stay curious, keep learning, and let the search for wisdom guide you forward. Have a great day.